طيب بسم الله الرحمن الرحيم. So last time we started to talk about from the beginning of this chapter about medium access control, and we talked about collision-based issues, Aloha, and so on. And then we deviated a little bit and we talked about reservation-based scheduling or reservation-based access control techniques, where we discussed explicit reservation and implicit reservation. We talked about different schemes in each of these. And then we said that we went back to collision-based techniques, because in reservation-based techniques we almost eliminate collision during data transmission. And then we discussed the special mode in Cdma CA, where we use RTS and CTS, and we have discussed how RTS, CTS can avoid the hidden terminal problem, exposed terminal problem, and so on and so forth. So this is basically the finite state machine that corresponds to the sender and the receiver for the case when we use RTS, CTS. So basically, the sender, when the sender starts to sense the channel, and if the channel is idle, then we said that the first thing we do is that we send RTS. So when we send RTS, so I assume that you are familiar a little bit with finite state machine in terms of the finite state machine is just a conceptual modeling tool which allows us to understand how certain mechanism actually works by dividing the functionality of that mechanism into states and transition lines, where each of these circles, they correspond to a particular state. Okay, so if I'm not transmitting, then this means that if I'm not, like, if I during the start of the communication, then I sense if the medium is idle, then what do I do? Well, if the medium is idle, then I can send an RTS, and in that case, I will move from an idle state into this is the sender. The sender will move into a state which is I sent RTS, therefore I'm waiting for CTS, which means that if I'm waiting for CTS and I received anything other than CTS, then that's not a right sequence, in which case I have to reject it. Okay? So the finite state machine divides the function into state and transitions. The transition here corresponds to a particular event that will happen while you are in that state. So when you are idle, if you decide to transmit, if you decided to transmit, this means that you have a packet in the buffer. So if you have a packet in the buffer, okay, then you can transition from that state into that state by sending an RTS. Okay, so this is so this is an event. So this is an event, and this is an action, and this is a state. So while you are in a particular state, if some event happened, then you can apply certain action. Based on that action, you can be either in the same state, which means that you loop, or you go into a different state. Okay, so for this particular case, if an event which is packet becomes ready in the buffer, then I send RTS, in which case I will have to move into a new state, which I'm now in a wait for CTS state. Okay, this state is really specific in the sense that When I wait for a CTS, I'm actually not doing anything else other than I'm waiting for CTS. So if a certain event happened, other than the fact that I'm waiting for CTS, then it will be not necessarily neglected. It will be different from what I'm waiting for, and based on that, either I have to send an error or I have to do something. An example of this is that while I'm waiting for CTS, a timeout happens because I cannot wait forever, right? So if I'm waiting for CTS and a timeout happens, what do I do? In this particular state, if a timeout happened, this is an event, right? So in that case, if a timeout happens, I send an RTS again, because this is an indication that the first one that I sent has been lost. Okay, and I keep doing that, and this is special for the case when I send an RTS, right? So if I send an RTS and I do not get any response, so actually someone might say, okay, if you send RTS and you do not get any response, then
you have to get back to the idle state.
But this will mean what? This will mean that you have to send an RTS, which will move you back to, right? So, and this is actually summarized by this loop here, which indicates that if the timeout happens, you send RTS again. Okay? If you are waiting for CTS and then you have an event which is you have received a CTS, okay? This is the event, right? Then in which case everything is good and you can send data. When you send data, you move to another state, which is now I'm waiting for an acknowledgement. If I'm waiting for acknowledgement, I received CTS, then I ignore it. If I receive anything else, I ignore it. So when you are in a particular state, pay attention to these arrows, because these arrows are the events that I'm waiting for. So while I'm waiting for these events, if I receive any other event, then I ignore it. Okay? So if a timeout happens while I'm waiting for an acknowledgement, then in that case, I will have to go back, or timeout happen, or a negative acknowledgement. A negative acknowledgement here might happen when you are sending the data, then the receiver will perform some error checking in the data, and then the receiver realizes that, well, the data has arrived, but it arrived in error. In which case, I will not send an acknowledgement in that case because the data is an error. So I send a negative acknowledgement. So if I receive a negative acknowledgement,
how do we sense an error data?
Yeah, there is like error detection codes while you're sending the data, you send some code with the data.
Parity checking.
Yeah, parity checking, exactly. So parity checking is one example of this. And based on this parity checking, you try to detect whether there was an error in the data or not. And the error happens, of course, for many reasons. Sometimes maybe the signal has faded a little bit, which has caused some of the zeros to be ones or some of the ones to be zeros and stuff like that. So in that case, the parity check will fail. When the parity check fails, we recognize that there was an error. Whether there was an error in the data or timeout, for me is the same thing. This means that the data that I sent did not arrive. Yeah. Okay, so in which case, for this, you have to go back to the wait for RTS state, and which means that this will allow you to go through this again, which means that you send the data one more time.
But Doctor, we are sending RTS now. It's RTS that I'm going to send you something?
No. RTS here means that I will send the RTS again. It's the same thing, like you say, you go here, which means that you send an RTS and go here, right?
Yeah.
So instead of going here and then going here,
It's like directly.
it's like directly,
Okay.
right? Because if you go here, you will, because you already have the packet in the buffer. You did not get rid of the packet because the packet is still there, right?
Mm-hmm.
So instead of going here and then you send an RTS, which will lead to the fact that you go here, so you might as well go directly. So that's what this arrow means. Okay? An alternative for this is, again, to get this into the idle state. But if you go to an idle state, you have to wait for another event of packet ready. Okay? Which already was there, and you did not, this event, you did not actually service that event yet. So instead of going into idle, which means that you will need another event to happen, okay? So you can just assume, you did not service the event yet. So you send an RTS and you go here. So that's for the case of negative acknowledgement or timeout.
After this, CTS should be sent by the receiver, no?
Yes.
There is no receiver in this.
Yeah, for me, for the sender, CTS is an event.
Which comes from anywhere.
It comes from anywhere,
Okay.
right? So this is the state diagram or the finite state machine for the sender, because here this is the one for the receiver. Okay? So if I receive negative acknowledgement or it's timeout, then I send an RTS and I go here. When I go here, I will have to wait for another CTS again to be able to send the data. Right? So when I receive the data and so on. So if I receive an acknowledgement, then and only then I go to an idle state, because now I have to wait for another packet ready event. Because if I go from here directly to here, this means that I will have to wait for the following packet to get into the buffer in order to serve the current packet, which does not make a lot of sense, right? Because if I go to idle, I have to wait for another event to happen again. But I did not service the first event in the first place. Are you following? So the original event that happened in the beginning is that packet ready to be sent, right? And all you are trying to do here is to service that event. Okay? So if I came to wait for acknowledgement and the acknowledgement did not come, or I received negative acknowledgement, this means I did not send the data successfully, which means I did not service that event successfully, right? So if I go here, if instead of going here, I go here, if I go here in the idle state, I have to wait for another packet ready event. And this packet ready event will be generated when I have another packet to come in the buffer, right? But the current one I did not finish serving, okay? So going here is not completely correct. It's not completely accurate. So that's why we send RTS and then we go here. Okay?
When we receive an
Only when we send an acknowledgement,
we can go there.
then khalas, this means that we have serviced that event successfully and completely, in which case we can go to idle and wait for another packet to come. So that's for the receiver side.
Just
We have only, go ahead.
for the receiver busy event from the wait to the idle. It's after having more than one timeout for the RTS, and then
That's a yes.
have to
That's a
go to
good
the
point.
idle.
Yeah, that's a good point. So in that case, yes. So in that case, I waited. There is a timeout. I sent RTS timeout. I sent RTS timeout. So this is a completely failure scenario where I cannot just keep sending forever the same packet over and over and over again. So this means that I tried to send the packet, so it failed first time. So you have to retry.
until
Once-
having efficient.
Yeah, until a certain point, and then you say, okay, the receiver is busy. The receiver cannot receive anything, so I have to ignore that packet and go to the next one.
Ignore the packet.
Yeah,
So
well, So when you ignore the packet, what will happen? When you
I
ignore the
have to
packet,
wait
this
for
is
it.
for, remember here we're talking about the MAC layer, right?
Mm.
So when I ignore a packet, what will happen? Well, it depends on the transport layer protocol. So if I have TCP will
I have to resend it.
will have to resend the packet, which will go again to the MAC layer, and I'll have to deal with it. But if you use UDP, then it's fine. But the packet is lost.
So when we get back to the idle state, I will just wait for another new packet.
Yes,
to
exactly.
come.
So this is that's the key.
And
That's the key.
The one will be
The
dropped.
current one will be dropped. Khalas.
Okay, tamam.
Yes. So when we get to an event, this packet is either sent or dropped. And that's why we did not go from here directly to here, because if we do this, this means that I did not finish serving this current packet, therefore I will have to wait for another event where I did not service this one correctly. For the receiver side, we have only two states. Either I'm idle, I'm not doing anything, and if there is, if I received an RTS, if an event received RTS, then I send CTS. When I send CTS, I will wait for the data. If I'm waiting for the data, and then there is a timeout or anything, then I go back to being idle, which means that I failed, and I wait for another instruction from the sender, for another clear instruction from the sender. So the sender is the main driver now. The sender is the main driver. So if there is any event, any failure, I will go back to being idle, and I will wait for another instruction from the sender. Okay? So the receiver case in that case is so this is a very special scenario where you receive one RTS. This means what? This is tricky. So I received RTS and I sent CTS. Right?
Yes.
But it looks like this CTS did not reach the sender on time or something. So I received another RTS.
Okay. From another sender.
From
the same sender.
From the same sender. So in that case, I have to declare receiver is busy. I will not do anything because I sent already my CTS before. If you did not receive the CTS, I will not. So this is a specific. I will not keep receiving. I will not keep sending CTS repeatedly.
But this means in the sender side that we didn't receive a CTS. Then we will wait until a certain time, صح? Then we will receive to a state where we cut back idle.
Or the CTS was received but not on time.
Oh, okay.
Okay. صح?
Right.
In which case, later on, if it's received, then خلاص, the sequence will go fine. Okay. So that's.
If it receives the data, then it should send acknowledge to the sender, no?
Yeah.
Yes. So this is. So when you receive the data, you send acknowledgement. If you have a timeout, okay, or you don't receive the data, you send negative acknowledgement. Okay. So if you have a timeout, you send negative acknowledgement. If you have wrong data, this means wrong data, like the data received but in error. In both cases, you send negative acknowledgement. But in all cases, you go back to idle and wait for another instruction from the sender, because then the sender is the main driver. Okay? But these, the timeout or data received successfully, these two events, if you see the corresponding arrows here, they correspond to two different functions being performed at the sender, right? So these, although this is the same arrow, but if that event happens, do this. If that event happened, do this, right? Although they are on the same arrow, but they lead to two different passes here, right, at the sender. So the sender is the main driver. Whatever the sender, asks me to do, I will do. But for me, for those two cases, I will go back to the idle and wait for another instruction. Okay? طيب. So polling mechanisms talk about the fact that, so we talked about reservations, TDMA, and we talked about FDMA, and we'll talk about CDMA and so on. So polling mechanisms are different. Polling mechanisms are, it's like we are in a meeting, and there is a coordinator for that meeting. And the coordinator is the one who runs the show, which means he can pull a certain person with any sequence that he or she wants. Okay? And this person is the one that will have access to the channel. Okay? This is slightly different from TDMA and FDMA and so on and so forth, right? Because for TDMA and FDMA, we don't necessarily need to have a coordinator.
Right.
We can set the time slots at the beginning and prefix them, or we use reservation, right, at the beginning, and send at the beginning that during this time, these are the slots, go. It's like I'm setting the meeting configuration for a duration of time, and then I leave it, and everyone knows where exactly the time slot that he or she should use, right? Polling is different from the fact that the coordinator needs to pull everyone based on a sequence up to him, right? And based on that sequence, each one will have not necessarily equal access to the medium, right? It depends on the polling sequence. But the key thing here is that we need a centralized coordinator. We have to. We have to have a centralized coordinator in that case, right? Another key issue, so in here, as you can notice here, we have to have a central terminal, okay? Or in other words, like a base station, okay? So this is the key here.
That is a coordinator.
A coordinator, right. A central coordinator, right. The other key here is this pooling sequence, okay? Because I can control the share of each one of the nodes based on the order and the duration where I pull each one. So I can pull you and give you access, okay, more than you, okay? If we have multiple people, I can pull not necessarily in order.
Okay.
So if I use the same order, this is basically technically round robin, right? So if I pull in the same sequence all the time, this is round robin, right? And in that case, I'll be completely fair and that's it. But who said that we have to be fair, right? So fairness is not always good in communication, by the way, right?
Based on the data.
Based on the demand of each node, right? Okay. So this polling sequence is the key here. So we have two choices. Either we have the coordinator to completely control this polling sequence, okay? In which case, the coordinator, based on his own discretion, he can select a specific sequence for pulling. Okay? That's one. This is actually the more common scenario, because pulling is all about using the coordinator. So if you have a coordinator to pull the nodes, and then you say, I don't want the coordinator to control the pulling sequence, then that defeats the purpose, actually. Surprisingly, there is a category of pulling mechanism which is called a randomly addressed pulling. And what that means is the sequence of pulling is in a way controlled by the nodes. The sequence of pulling is implicitly controlled by the nodes. How? Basically what happens is that the nodes, each node will generate independently a random number. Okay? So we are like 10 people. We are like 10 people. Okay? So the nodes will be asked to then select a random number between 1 to 10. And this will be the order of pulling in the next period of time. So in this round, you happen to be number 1. I happen to be number 10. Right?
Okay, but
In the
what
next
about
round,
information?
I might be 1 and you might be 10. Okay? So this is an implicit pulling order which is controlled by the node, because we generate the random number. So each one will generate the random number independently, and then we send it to the coordinator, and then the coordinator will take that, and then will pull the nodes based on these numbers. Is this completely fair? Basically, there are two issues here. The first, is this really completely fair or not?
Because everyone will want to send first and everyone can select on number one.
No, you can't. You have to generate a random number. It's not it's not that you generate any number. You generate a random number.
Okay.
But does this random number generation guarantee the fact that it's completely fair? The answer is yes. If all the nodes use uniform distribution of generating the random numbers, then it's completely fair, as long as they all use the same distribution.
Suppose I have more data to send when compared to another node.
Not the order. This is only for.
Yeah, so in that case, this is an issue, because being completely fair, although you have more data than Abir, then this might not work the best for you, because you will have the same share of accessing the channel similar to her, which means that, because in this case, because it's randomly pulled, it's completely fair in a way. It's just that we try to change the order every time. Okay,
But it's not
using
random.
random actually makes it completely fair. It's similar to the back-off procedure in Cdma CA. Remember, we talked about back-off procedure. We said that if there is an error and two nodes collide, right? So we back off. What is back off means? Well, each node will generate a random number, and each node will wait for a certain period of time corresponding to this random number. Okay, so basically we will generate a different number. But why is it random? Well, it's random because for this time I may actually select a number which is different from yours, in which case maybe you will gain access to the channel before me, or I gain access to the channel before you, in which case we try to avoid the collision next time, right? But another reason that this is random is that over a long period of time, it will be fair. So randomness always guarantees the fact that in most of the cases we'll generate a different number. But this different number will change, okay, throughout the time, so that if you select a high number this time, chances are next time you will select a low number. And if I select a low number this time, chances are I will select a high number next time. So on the average, it's like we are jumping back and forth so that we will be different, but throughout a long time, the probability that you select 1 is the same, like you select 2 is the same, like you select 3, and the same, like you select 4, same thing all the way to 10. You see what I mean? So for this time, you select 1, I select 10. So next time, you select 10, I select 2. Okay?
But the probability
Next
of
time,
putting-
you select 3, I select 8. And we keep juggling, okay? So over a very, very long period of time, you will see that you selected 1, the same number that you select 2, the same number that you select 3, the same number as select 4. But in each time slot, we were different. So this is the good thing about generating random numbers, is that we try to be different every time, but along a very long time horizon, the probability is we will be fair, because this time you select high number, I select low number. Next time you select high number, you select low number. So we keep juggling back and forth.
This selection we cannot control, no? It is randomly generated.
Randomly generated.
It's
It's implicitly controlled by the nodes, right? And that's how you control the polling sequence. So this one is actually very fair. So the two issues are, you cannot actually provide any quality of service in that particular mechanism. Why? Because being random, this means that even the nodes, in a way, do not control because they generate a random number.
Doctor, if I have more data to send, can I always generate a high random number so that I have to send like?
So in that case, you are cheating.
Yeah.
In a way, you are cheating. Why? Because, well, remember, controlling the polling order, it does not mean that you can send higher data. Remember, here we are controlling the order of polling, not the number of packets that you send. Right? So as long as you are generating one number and I'm generating another number, this means that we are trying to avoid the fact that we get pulled at the same time by generating a random number. There is a very slight chance, by the way, that two nodes will generate the same number, random number. And that's another issue. But hopefully this will not happen very often.
But once we generate a random number, a time slot will be given for us to send the data.
Not a time slot will be given, no. A polling signal will come from the base station when we are asked to send. There is a slight difference here. Remember? Every time we'll wait for his polling signal before he can send anything.
So once we get a polling signal
it's
back,
slightly different from time slots, right? In other words, polling is totally asynchronous. It doesn't require any synchronization. But Cdma requires synchronization between the time slots, right?
Okay.
But polling is like, you have a coordinator, I give you the mic, please, you can talk now. This can happen at any point in time. It's up to me.
So how
But Cdma, we agreed in a meeting, you will talk first, then you will talk and if every one of us has a specific time slot. When this ends, that's it, go next. So the duration is predefined and also the order is predefined.
Here the duration is predefined but not the order.
The polling, for polling, neither are defined. Because it's up to the coordinator. I'm polling you. When I poll you, I will tell you you can talk for 10 minutes.
No, I mean the random polling.
For random, yes, for random, the nodes implicitly control the order.
Okay, what about the time?
No specifics. So
So
it's
it
up
could
to the
be-
coordinator.
Okay.
The
does that
duration,
mean that
it's
it's
up to the
different for all?
coordinator. So maybe you're right. Maybe if you have more data, I can pull you, but I can give you more duration.
Yeah, that's it.
So
Yeah.
I could do that. I could do that.
So the coordinator can check the amount of data to be sent by different stations, and he can allot time and duration and order as per the requirement.
Right. So here, terminals ready to send can now transmit a random number, But when we have multiple nodes, generate a random number and they send it to the base station, well, we have the same scenario now. We have multiple nodes trying to access the channel at the same time. So either we have to use Aloha in that case, right? Or we use a collision-free environment. So in this particular randomly address pooling, so in randomly address pooling, which is abbreviated as randomly access pooling, okay? So for this one, we use a collision-free transmission between the nodes to the base station, in which case we either use Cdma, and we'll talk about Cdma again now, or we use FDMA, which means that when we send the random numbers, we can send it on different frequencies. So for the uplink, each node has a specific channel to send on. And the base station will receive all the random numbers from all the nodes. And then when it receives all the random numbers, it pulls every node based on the value in this random number. Okay. So you're 1, you're 2, I'm 10, and so on. Okay. Or we use Cdma. In other words, for RAP, we actually have to use a collision-free medium access control when we send the random numbers, okay? Because this requires the fact that so of course I can improve this by allowing the nodes, instead of sending random number, send your demand, right?
Right.
So instead of sending a random number, I ask you, please send your requirements. So you describe to me what your requirements are in terms of how much delay you want, how much throughput you want, what type of traffic you want to send, whether it's video or audio. And then from these values, I can then run my algorithm and my intelligence. And based on that, I say, okay, so I better pull Abir first before you, because she has some more strict delay requirements. Okay? So if you have more strict delay requirements, then I put you in the beginning, for example. Okay? If you have more throughput requirements, then it doesn't matter the order, but I should give you more duration. So the order and the duration can be extracted from this information.
Each mobile, for in this case, Doctor, if you imagine communication, mobile communication, these nodes are the mobile devices and...
Right.
Huh?
Right. And they generate these random numbers independently, right? So there is a slight chance, as we are saying here, there is a slight chance that you can have collision when two nodes, they happen to generate the same random numbers. But this will be unlikely. This will be highly unlikely, okay? All right. So this is the wrap or randomly access pulling, and this is the pulling mechanism. This is called ISMA, or inhibit sense multiple access nodes, and this is used as part of the AMPS. AMPS is first generation wireless, and this is these standards are mainly analog standards. Okay, so how do we control the access to the medium? Because we're talking about medium access control here, and here the medium access control is done in a very primitive way. What happens is that the base station here will send a busy tone signal. The busy tone signal is a signal that the base station sends on a specific frequency, so that all the nodes can go to that frequency and listen to this busy tone signal before they decide to transmit anything. If this busy tone signal is there, then they don't transmit. Okay? If it's not there, then any node that has data can send at any point in time, which means that we will use Aloha kind of transmission if the busy tone signal is not there. So this particular mechanism, or ISMA, so this ISMA will allow the nodes to use Aloha to access the channel. Okay? And if one node has access to the channel, the base station will, once it detects that someone is sending, what happens is that it sends a busy tone. When it sends a busy tone, all the nodes
Stop sending.
will stop sending anything except the one that's already going, right? Which means that it's the medium access control here is kind of controlled Aloha. So what happens is that, remember, we have a signal, so we have a specific carrier frequency. You have a busy tone. The busy tone, whenever you see the term busy tone, this means a signal in another frequency. So this is the carrier frequency. This is the busy tone frequency, which is a separate frequency from the transmission of the data. The base station can detect this transmission, and based on that, the base station will send a busy tone on a different frequency range, which means that the busy tone will continuously be there as long as this transmission is going. Once this node stops sending to the base station. The base station will detect that the node has stopped sending, and then it will stop the busy tone. Once it stops the busy tone, what will happen?
The other nodes.
All the nodes will have the freedom to send. Any node will have the freedom to send.
But the first one.
The first one that will try to send using Aloha,
And then it will send.
the base station will detect that there is a transmission going, so it will turn on the busy tone again to stop all the other nodes from transmitting the signal. So in other words, once the busy tone is stopped, it's Aloha. Once one node starts to transmit and the base station detects that there is one node transmitting, and remember, once a node starts to transmit, I will fire the busy tone right away. So I will prevent any other node from starting the communication. So although the probability of collision here is there, but it's low in a way that once the node starts transmitting, the base station will detect that a node is transmitting, and it will turn on the busy tone. Once the busy tone is turned on, then no other nodes will send anything.
Doctor, this is FDMA TDMA, no? If you compare with mobile.
This?
No, when in mobile communication, it's FDMA TDMA.
Right,
yeah?
exactly, yes.
So if you bring this case into that scenario, many nodes can be given access during one maybe one frequency.
This particular example?
Yeah, because there may be thousands and lakhs of mobile stations, nodes trying to access the BTS.
Okay, so you are talking about combining this with, so in other words, in GSM or in 4G, you have resources in terms of specific frequency and a specific time. And this resource gets assigned to nodes. So instead of assigning this resource to one node, you can assign it to a group of nodes, and these nodes will use that technique, to gain access to this particular resource. Is that what you're saying? Yeah, in
so
that case it's
possible.
possible.
One
it's
second,
possible.
Thousands of mobile station can access.
But in that case, you need the base station to be able to support the busy tone. The busy tone is out of band. Remember, it's an out of band control signal. Because what you are talking about is assigning TDMA and FDMA happens through like some in-band controlled signals, which has nothing to do with the busy tone. Okay?
So
but
where is
here,
this applicable in real case scenario?
This is used, remember, this is used in amps, which is the first generation wireless. Like starting from GSM, which is second generation, this is not used anymore.
Oh, this is presently not used anywhere?
No, currently no. Yeah, so ISMA has been used in first generation wireless, which is amps, but now it's not being used anymore. Okay. However, here we're talking about a specific concept or a specific mechanism, which, as you say, like someone might come today and say, I can integrate this with 4G or 5G and prove to you that this will enhance the performance even more. Well, okay, show me. It's just a mechanism. So in this chapter, what we talked about is like we have diverse set of mechanisms that will allow us to control the access to the medium. Okay, that's what we're talking about here. But we say that, okay, this mechanism is used for this standard, this mechanism is used by this standard. So we, as you mentioned, like Wi-Fi uses Cdma CA, so we know that. For your case, TDMA and FDMA is used by second generation or actually third generation and fourth generation, except that for 4G, and instead of using FDMA, we use OFDMA, right? We use OFDMA, so it's subcarriers. But it's still the same. I mean, as far as MAC layer is concerned, it's the same concept. You have a small resource, in that case for OFDMA, it's a very tiny small resource, and you assign that resource to a particular station or a particular node. It's the same concept.
But for every single node, it can't send a busy tone. No, it should be for 1,000 nodes. If the entire channel is busy, then only if the 1,001 node come, then only it can send a busy tone, like, because it is packed with
No,
time.
it's not. Well, remember, busy tone is not being sent by nodes. Busy tone is sent by the base station to indicate that the medium is busy.
Yeah.
And this busy tone is supposed to be heard by all the nodes that are accessing this particular base station. And remember, we did not even talk here about the multi-cell scenario, because AMS does not support multi-cell scenario. Okay, and that's why this primitive or this sample mechanism can work fine for AMS, but you don't know how the busy tones will work if you have multiple co-located cells. We didn't talk about that.
Even a single cell.
But this for single cell it might work fine, and that's why they use it for AMS, because it's simple. So it's basically aluha as long as there is no busy tone. If there is busy tone, then stop. That's it. So before you send, listen to the busy tone signal. If it's there, do not start. If it's stopped, then send. So basically it's aluha, but the control signal will allow us to reduce the collision, but not eliminate it. Because there is a chance that two nodes will start exactly at the same time, in which case the base station will not be able to detect that there is one, so it sends the busy tone before the other starts. So before it sends the busy tone, two have started at the same time. So they will collide. But hopefully, this is highly unlikely.
After one base station catering to one particular cell.
Right.
That cell may contain thousands of devices,
right.
nodes.
Right.
So if suppose this node is communicating with the base station,
right,
and it sends a busy tone to all the other nodes.
No, we didn't talk about that. No, the busy tone is not being sent by any individual node. It's only sent by the base station.
Yeah, base station.
So if a node tries to send at this point in time, and before any other node tries to send, the base station has detected that this node is sending. So it will send an out-of-bound busy tone signal.
Yeah.
So that before any other node starts to send and collide with this, it will hear the busy tone signal and it will stop.
Okay.
It will stop the transmission before it starts. Okay? So that's what happened. So what is your scenario? I didn't see. Okay.
Actually, there are 1,000 nodes. So for each and every 1,000, each and every node, the BTS has to send this busy tone. Like,
it's broadcast. It's wireless. Remember, it's busy tone is just broadcast signal. So before any node starts any transmission, all it needs to do is just to listen to this particular frequency range if there is any busy tone signal. And busy tone signal, usually it's a high power signal sent in a specific frequency range. That's what busy tone is. If there is any signal in this busy tone range, then do not initiate any new transmission. If there is none, then you can send right away, which technically means aluha. So any node can send at any point in time. It's حتى unslotted aluha. Okay, so there's no even time slot. All right, so CDMA, we talked about CDMA before. I assume that we're familiar with it, except that this time we'll try to take some different approach in the sense that we will go through some numbers and we'll see exactly the sequence, how CDMA is being sent. So we know that CDMA, all terminals send at the same frequency at the same time, but use a different codes. There are two conditions for these codes. Remember, these codes are sent using or are generated using two conditions. One, these codes are mutually orthogonal. That's very important. So if you have, how's this? Well, if you have like let's say we can use some numbers. So this is a code, example of a code, 0, 1, 0, 1, 0, let's say. Okay, so this means that the other codes should be 0, 1, 0, 1, 0, 1. Those two codes are orthogonal in the sense that if you multiply, the answer will be 0. This means that they are orthogonal, right? So this is the first condition. The second condition, codes, individual codes, have high autocorrelation with itself. This means that each code on its own has very high correlation with itself. What does this mean? This means that if you multiply the code by itself, the answer is very high. But if you multiply this code by any other code, the answer is 0. So this means that these codes are mutually orthogonal, but individually highly correlated. Type. Is this condition fulfilled? Is this second condition fulfilled in these two codes? Well, maybe. If you have this code and multiplied by itself, what is the result?
The first code?
The first code.
By itself it will be like 1 times 1 is the same.
Same.
Yes, but 1 plus 1 plus 1, right? So you multiply, and then you get the summation of everything, right? So 1, 2, 3, right? And this one, 1, 2, 3. Can we design these codes in such a way that we can have higher than 3? Because if that's the case, then this is the way to go. So it turns out that 1s and 0s are not very good in doing this. So we better use -1, -1,
Instead of the 0.
and -1. So if we do it this way, let's see, can we actually get some, if we get the autocorrelation for these codes with itself, okay, what is the autocorrelation in that case? You multiply the vector by 6, bravo Ali. So 6. So instead of 3, it becomes 6, right? So this means that really, usually in Cdma, we better use 1 and -1 rather than 1 and 0. So that's one thing, because if we can do that, then the autocorrelation for these codes with itself is very high, and that's what we need. And I'll tell you why later on. When you have high correlation for these codes with itself, then this will allow you to mitigate or to avoid interference much more efficiently. And I will tell you why later on. Okay. But then you have to preserve, while you're doing this, you have to preserve the orthogonality. Okay, which means that in that case, the location of 1s and -1s have to change, because here, 1, this will be -1, this will be -1, this will be -1, this will be -1, this will be -1. So if I multiply them by each other, the answer will not be 0. The answer will be -6 in that case. So we need to change the, but we could do that, right? So you can change the 1s and 0s so that you can have 1 plus 1 plus 1 minus 1 minus 1 minus 1. So the answer will be 0. So easily we can do that. So we can preserve the orthogonality but increase the autocorrelation, right? So these are the two conditions. So codes needs to have needs to be mutually orthogonal, okay? But highly correlated with itself.
Doctor, for any codes,
Mhm.
if we multiply by itself, it will always be 6, no?
Right.
Hmm?
Right.
But
And that's what we want.
Of minus 6.
Hmm?
Then where comes the case of minus 6?
Oh, if you multiply these two codes together, if you because as we said, يعني in that case these two codes will not work, will not fulfill the two conditions at the same time. If you want the two conditions if you want to have 6 as autocorrelation, which is the objective, then you need to change the location of ones and minus ones. For example, you can have 1, 1, minus 1, minus 1, and enough like this. So in that case, you can have minus 1, 1, minus 1, and 1. Okay? So the autocorrelation for each one is 4, right? So we know that. So 1 times minus 1, it's minus 1. 1 times 1 is 1, right? So this will cancel. And then minus 1 times minus 1 is 1, right? And minus 1 times 1 is 1, so this will also cancel. So these two codes now achieve both conditions, right? They can easily achieve the two conditions. The autocorrelation with itself is the maximum, which is 4, and that's what we need to do. And they are mutually orthogonal. So you can design these codes, and if you have a code of a length 32 and sometimes it's 128, luckily there are some people who have driven or provided some systematic procedure for how we can generate these codes so that we can achieve both conditions easily. Okay, one is I think it's called Barker. So there's a guy called Barker who has invented a way to generate these codes, and also we have Hadamard. So this guy as well has created there is a Hadamard matrix, and this matrix actually, each row in this matrix fulfills those two conditions. So you can generate a huge matrix, okay, like 32 by 32, so that each row in this matrix actually fulfills those two conditions using the ones and minus ones. Basically, what he said is that you can have 1, 1, 1, minus 1. So these two simple rows, they fulfill the two conditions, right? Mm-hmm. So you can multiply these codes. So you can have 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, and minus 1, minus 1, minus 1, 1. So if you look at those 4 rows, any two of these rows are orthogonal. So you can easily double this every time. So instead of 4, you can make it 8. Instead of 8, you can make 16, 32, 64. You can multiply this, and in that case, you can take that block, repeat it 3 times, and in the 4th time, multiply by minus 1.
Okay.
So the result will create 8 by 8 matrix where all the 8 rows are mutually orthogonal and highly correlated. Mm-hmm. Very easy, very simple. Okay, so those two conditions have to be fulfilled. So now, going back here, so each sender has a unique random number, and it's not random number. It's not completely random. So it's random in the sense that you select any of these codes, any code, it doesn't matter, as long as these codes are mutually orthogonal, right? But you can select any node, can select any code, okay? And before you transmit your data, okay, multiply your data by this code. So multiply the data by this code. So then, when you send at the same time, at the same frequency, what does this means? This means simply, we can just apply the simple concept. So you have, let's say, node A sends data AK, for example, and node A multiplies this by a code which is AC. Okay? At the same time, at the same frequency, which means that it's superimposed, or in other words, anyone who is receiving this data gets the aggregate of this data, right? The summation. Node B tries to send any data, right? And it uses a specific code for node B. Node C sends the same thing, any data, with a specific code CC, okay? All right. So you are a receiver, you are trying to receive, let's say, you are trying to receive, you select whatever data you want to receive. You want to receive the data from A or B or C. If you want to select the data from B, okay, you use the code for B, which means you use BC. So there is an agreement between the sender and the receiver on on this particular code. So as long as any receiver knows the code for receiving data from B, it will use that code. What does this imply? Let's see. So you get the aggregate signal, right? You get the aggregate signal and you multiply it by BC. Type. Let's do it mathematically using like linear algebra. So AK times AC times BC. What is this? Zero, right? Because they are mutually orthogonal, right? And BK times BC times BC. This is the autocorrelation for this particular code, which is really high, right? So you will receive BK multiplied by a large number. Which means that you get a very strong signal. And that's why even if you have any interference, this will allow you to overcome the interference. Okay? So this is multiplied by BC squared. And plus, of course, plus CK multiplied by CC multiplied by BC. And that's also a 0. So this will be 0, this will be 0, and this will be very high. So that's the idea. This is the idea of Cdma, basically. Okay? All right, so going back here, so the receiver can then tune into this signal if it knows the pseudo-random number, اللي هو ايه? The code. What is the disadvantage? Well, the disadvantage now is that the receiver needs to maintain all these codes. So if you want to receive from B, you need to use the code of B. If you want to receive A, you need to use the code of A, and so on. So each node will have to now maintain codes for all the other nodes, right? And if you want to receive from this, you have to use the right code. So this actually complicates the design of the receiver. So the receiver for Cdma is highly complex because you have to maintain, in some cases, imagine if you have thousands of nodes.
Then you have to have
1,000 codes. And you have to control that at the physical layer, which is significant. The other thing is what we talked about before. We said, and we will talk about it again now, all signals should have the same strength of receiver. This is the near-far effect. Remember if we said this is the near-far effect? So, for example, if you have if you're trying, if the receiver is actually receiving the aggregate data, the scenario that we just talked about, that this data have the same level more or less. If some data has, if some of these signals have very low signal and the other one has higher signal, if you are trying to receive the signal from the low one, then the other one will create more interference for you, which may not be recovered by the autocorrelation. So we said that the autocorrelation will help us, but in some cases, if you have some of these signals are very low and some are very high, okay, then this high signal might affect the reception. An example of this is that as we said before, for Cdma is like when you have two people are communicating using Chinese and other two people are communicating using Arabic, usually this creates some kind of interference. But if they are talking two orthogonal languages, which is the codes that we talked about, this communication can go concurrently, and each one can listen to this and be able to distinguish Chinese from Arabic. However, if Arabic happens to have very, very strong signal, then although you have orthogonal communication, but because the signal is very high compared to the Chinese, then the interference will affect. So this is what we call a near-far effect. The near-far effect. So in order for Cdma to work fine, then the receiver, any node that receives the two signals, needs to be able to receive them more or less at the same level. So always when we talk about Cdma, we have to combine Cdma with some power adaptation. So if the receiver has one node close to it and the other node is far, okay, then the node that's far needs to adjust its power when it sends to that receiver, so that it more or less balances out any kind of interference that happens from the closer nodes, right? So nodes in Cdma have to always use power adaptation, adaptive power transmission. So the receiver is highly complex in terms of design because of the fact that we have to maintain all the codes and also because of the near-far effect. Okay.
The receiver in this scenario, how can receiver be multiple in number, like thousands of number?
Because if we have imagine like if we have 10 nodes, right? 1, 2, 3, all the way to 10. Okay, if I'm one of these 10 nodes, I can receive data from node 1 or node 2 or node 3 or node 4 at any point in time, right? So in order to receive data from node 1, what do I need to use? The code for node 1.
Okay. This is
right? If I want to receive data from node 2, then I have to use the code for node 2. Then technically each node has to have all the codes for all the nodes, right? Because I have to have mine as well to be able to send.
Okay.
Which
communication the same level, not from a base station to a node. Like this is intercommunication within the same level, not from a BTS to a base station.
Right. So this talks about like if we have like an ad hoc scenario. Yes, and that's why Cdma is being used for 3G on a very large scale. Why? Because we don't have this issue. We don't have this issue because we always communicate to the base station, and that's a good point. We always communicate to the base station, right? So all we need to have is, so the base station needs to have the codes for all the nodes, right? And that's possible because the base station is highly complex. But the nodes, each node will be assigned only one code. That's it. And then it's up to the base station to use the code whenever it wants to send this particular node specific data. So if the communication happens in a star-like topology, then Cdma is highly possible and it's relatively efficient. Okay. Ooh, wow. It's 2:35. Okay. Oh yeah, we started late. Right?
Yeah, we started.
1:20 we started.
Right, okay. All right. So the advantage is that, well, basically we can work concurrently, we can send at the same time, at the same frequency, and also remember we have very large space. Of course, we cannot use all the vectors in this space because we have to fulfill the two conditions. So if we can generate, if we have 32-bit long vectors, well, we can generate up to 2 to the power 32 different codes, right? So we know that. But 2 here, 2 to the power here means that 1 and minus 1. So 2, we have 2 states, 1 and minus 1. But not all of them will fulfill the conditions, right? So we have large space, but we have to pick from that space the codes that fulfill that condition. And it turns out that we have good number. We have good number in this domain that will allow us to have large number of codes. The other thing is that Cdma actually turns out to be able to facilitate the security because you can use these codes in a way as keys. So in a way they can work as keys. And in order to receive the data from one node, you need to use that particular Cdma code, right? So it can be perceived as a key, okay? So you can hide that code if you want, in which case you can facilitate security without actually doing anything. You don't have to do anything from the application layer. You can just hide that key, and as long as the base station and the node they agree on that code, they can have so that the data is in a way encrypted.
So you can go to an operator and buy a code for us for private communication?
I'm not sure if that's possible, but theoretically speaking, yeah, it's possible. But the base station and the node, or any two nodes, they need to agree on that number, and they need to be in sync in generating that number, because we will see now another issue, another feature in this code is that we said that the code, for example, these codes do not. But if we have مثلا one, so 1, 1 and 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, and minus 1, minus 1, minus 1, 1. So these are the two codes. If I take this code and shift it one digit, which means that I will take this minus 1 and I will bring it here and I will shift this down. If you do this, you will find that you technically generated another code in this matrix, which means that when you multiply the two together, you will get 0. What does that mean? This means that if the receiver decided, for some reason, out of miscommunication, to have a shift in the generated code by one digit, okay, when you multiply, you get 0.
For all of them.
For all of them. So this means what? This means that these codes have to be generated between the sender and the receiver highly in sync. Because if you shift this a little bit, when you multiply, it's as if you are multiplying by an orthogonal code. Or you will get in that case something very close to 0. So you will not be able to distinguish this data. So this should be one of the disadvantages actually, is that as part of the receiver, not only do you need to agree on the code, but you also need to synchronize when exactly you generate that code. And these codes are continuous in the time domain, so you need to make sure between the sender and the receiver that they are in sync. Because if they are not, then when you try to multiply, you get something close to zero. And this is what we will see in a minute here. So this is...
I just have a question. The scenario that we are talking about here is between nodes, where we don't have a base station. So all the codes between the nodes.
Technically, Cdma works for both.
Because
Yeah, but with the scalability in terms of the complexity of the receiver will be high. The receiver will have higher complexity for the case of ad hoc, because in that case you need to have all the codes for all the nodes. But if you have nodes and you have a base station, then the base station needs to have all the codes for sure.
Mm-hmm.
But the node, one node may have only one code.
Its own code.
Yeah, its own code. That's
Okay.
it.
For the security issue, it's not for the ad hoc scenario, right?
Well, again, this is conceptually by the fact that these codes may act as keys, because as long as you're not sending the actual data, you are sending a processed data. This has some privacy, built into it, right? Because if you listen to the channel and get the data, what you have actually achieved is not the actual data. It's a data which is coded by the Cdma code.
But I do have all the codes. So
If you have all the codes, then there is no privacy there. خلاص.
Oh, so it's only when the base station have all the codes, we do have the
Yeah.
security.
So nothing is hidden from the base station, of course. If you have all the codes, then you will be able to select. You select where you want to receive the data from, and in which case there is no privacy there. But what we're saying is that if you don't have the code for any particular reason, طبعا in that case the base station has everything. But if any other node wants to listen to a communication that happens between another node and the base station, this is the eavesdropper. The eavesdropper, that's what it does, right? The eavesdropper listens to an ongoing communication. Well, if it listens to the communication in that case, if it does not have that code, Cdma code, it won't be able to receive anything. Okay. So this is a numbered scenario where A has data of 1, and this is the key. But as we said, in order to make the autocorrelation high, we will convert everything using ones and minus ones, as opposed to 0 and 1. So here we will assign 0 to -1, and we'll assign 1 to 1. You can do the other way around, and it will work just fine. There's no problem. Okay? So sending signal, the signal that we send in that case is A, the data of A, multiplied by the code. So in that case, if you send 1, this is the actual signal that you will send. What that means is that you get the actual signal and you spread it. So instead of sending 1 bit, you send 5 bits. Okay? So what did we do here? We did not... Well, we facilitate the concurrent transmission. So we spread, but in that case, we will allow 5 nodes to send at the same time. So instead of sending 1 bit for a short period of time, and then we get the other bit for a short period, because if we do this, then they will overlap and collision will happen and things like this. And instead of doing this, we'll spread. Okay, so there's no issue sending at the same time, but you have to have this code. So we facilitate the concurrent transmission. So we facilitate the concurrent transmission in that case. So sender B wants to send 0, and in that case, this is the code. So if you convert that to -1 and 1, and if you multiply this by this, the answer should be 0. Okay, so if you multiply the code here, remember this is 0, so this is -1. So the actual vector here, the actual code is actually 1, 1, -1, 1, -1, 1. So this is BK, right? So this is BK. If you multiply BK by this, the answer should be 0. Okay? So if you send both signals, remember A is sending A is sending 1 and B is sending 0. But both of them are sending these two signals, which is the multiplication of the code by the data. When you get the actual composite signal, this is what you get. So the receiver will receive this. So you get the summation -1 minus 1 is -2, and then 1 minus 1 is 0. So you get either -2 or 0 or +2. Okay? So if at the receiver you want to receive the actual data of A, then you multiply this by AK. And in that case, AK is this. So if you multiply this, by actually this, so -1 times 2, -1 here, times -2 is actually is 2. And then 1 times 0 is 0. And then -1 times 0 is 0. And then -1 times -2 is 2. And so on. And you sum all of this. When you sum all of this, this means that you get the actual data multiplied by a very high number, which is 6. Okay? So as long as this number is higher than 0, then the actual data was 1. If the number, you can try the same thing and multiply by BK. And in that case, BK is this. You will see that you will get here -6. Which means that as long as it's below 0, then the actual data was -1 or 0. So that's how it works, basically. This is what we did.
So for sending 1 bit.
Yeah, we're sending 1 bit. So that's why we get the summation of all of this. And if the answer is above 0, then it's 1. If the answer is below 0, then the original data was 0 or -1, because we have mapped 0 to -1, remember? And we have mapped 1 to 1, to +1. Okay, so that's how it looks like in the time sequence. So here, remember, the code in that case is continuous in the time domain. Okay, so here the code is continuous. So this whole code is mutually orthogonal with the code of B. Okay, so in the time domain, this code is generated continuously. And as long as at the receiver side, the code is generated with complete synchronization of this code, then you can be able to receive the data, whether the data is 1 bit, 2 bits, 3 bits, whatever. Okay, so here in this example, remember that in this example, 1 is mapped to -1. So here, yes, so in this particular example, because as you can see, this here, signal A starts from -1 here, right? So here, 1 is in fact mapped to -1, and 0 is mapped to 1.
So where does it start from -1?
Because,
if we, okay.
okay, so this means that if you have data of 1, this is mapped to -1 signal. Okay, same thing here. Key of A. If I want to get this key is in fact here is 1, which means that the actual code had 0, and then 1, and then 0, and then 1, and then 0, 0. Here.
So sending 1 bit requires 6 clock cycles.
Right. Yeah. Which means that you can facilitate the transmission of 6 different nodes to send at the same time. Okay? So you can have a composite signal of 6 different signals from 6 different nodes. Okay? So that's the key here. So basically, what you do is that you get the multiplication of this, and this is the signal that you will send. This is AS.
So here AS is the composite signal from 6 different
From
nodes.
no. AS is the signal that node A will send out
Okay.
after it applies the CDMA code.
Okay.
Okay? So then AS may get accumulated with BS, with CS, with DS, and so on. Okay?
Similar 5 more signals.
Right.
In one, so in 6 clock cycles, 6 signals.
Up to 6,
from-
yes.
yeah,
Up to 6, yes. Remember here, one details here, that the code doesn't have to be the same for each bit. This is a continuous sequence of codes. You see, like it's 0 1 0 1 0 0, and then it's 1 0 0 0 1. So it doesn't have to be the same and repeated. We don't have to have the same code repeated for each bit. It's a continuous sequence of bits, but the condition is fulfilled on the entire code. So from here to here, it should be orthogonal.
But
So this
6
code
bit-
has a length of 18 bits in that case. And this code should be orthogonal with the code from B.
So this 6 bit is called one Welsh code. Huh? There are 63 orthogonal codes in CDMA, some Welsh code or something called.
This is called 6 here is called the spreading factor.
Okay.
The spreading factor. But the code is the entire 18 bits.
Bits, okay.
Right. The entire 18 bits have to be orthogonal.
Okay.
Remember that. The entire 18 bits have to be orthogonal, not just the 6 bits. Okay? So if you get the multiplication of AK with BK later on, which will come in the next slide, for all the 18, it's orthogonal. Which means that in that case, I need to receive all the 3 bits from A, or all the 3 bits from B, or all the 3 bits from C, and so on. But here is what we call a spreading factor. We call it a spreading factor. So how many
Bits I need to
bits we
present
spread
one.
each bit? It's 1 to 6. In that case, it's 1 to 6. We call it the spreading factor. So B here, so remember this is the signal from A. And here we have B, and B here sends 1 0 0. And this is the code from B. This is BK. So BK here is this. So when we multiply B by data from B, this is what we get as BS. Okay? Remember, this is AS, and this is BS. Okay? So when we add this to this, so -1, and this is -1, so the answer is -2. 1, and this is -1, so the answer is 0. And -1, and this is -1, so -2, and so on. So this is like the composite signal. This is AS added to it BS. So that's what the receiver gets. Whether it's 2 or 3 or 4, it doesn't matter. Actually, the more signals I get, the better, because in that case, the autocorrelation will be higher and higher. Okay? So this is AS plus BS. Okay? So here, remember, this is data from A, and I'm trying to receive data from A. That's why at the receiver, I will use AK. So that's the data that I'm trying to receive. Okay? So if I want to, and this is AS plus BS. So this is the composite signal. So if that's the composite signal, I use AK. And AK, this is what it looks like. So I multiply this by this, and the answer is minus. Multiply this by this, and the answer is positive, and so on. So this is AS plus PS times AK. Okay? So this is 0, sorry. This is 0 multiplied by -1, so the answer is 0. So this is minus 2 multiplied by plus 2, so the answer is minus 2. This is plus 2 multiplied by minus 2, so the answer is minus 2, and so on. So I get the multiplication of this. Okay? So I'm done. So now, from this signal, I need to recognize whether this bit is 0 or 1. That's what I need to do now. And to do this, what happens is that they use an integrator output. What does that mean? This means that you start from here, you start from 0, and then if the answer is minus, you add this. Yani it's an integrator or summation, in other words. Okay? So you add minus 2. So you go to minus 2. And then you add 0, which means that you stay the same. And then you add minus 2, which means that you go down. And then you add minus 2, which means you go down. And then you add 0, which means you stay the same. And then you add another minus 2, which means you go down. So clearly, as long as you are in the negative side, this means that it's minus 1. And since we have, since we mapped 1 to minus 1, so the original data was 1. Same thing you do on this bit, and same thing you do. Okay? So that's what you do. So, of course, if you need to do it with B, the exact same thing. You do the integration. Integration is basically, in hardware circuit integration, is like it's like you are summing. You're getting the summation of all these signals, of all these values in the time domain. Because remember, all these 6 bits correspond to 1 bit of data, right? Right? So that's how you do it. So you use an integrator output. So minus 2, and then 0, and then minus 2, and then 0, and then minus 2.
It's
Again.
an analog signal, huh?
Yeah, it's like an integrator is like an analog integrator. It actually gets the summation of all the 6 bits. Okay? So minus 2, 0, and so on, and that's how you do it. So it's minus, so the original data was 1. So here it's plus, so the original data was 0, and here it's plus. So this is the data of B. So if you happen to use a wrong key, and the wrong key in that case, by the way, is just, I think this is AK or BK, but it's just shifted one slot. So this key is nothing but AK or BK, but it's just shifted 1 slot. Okay? So if that's the case, you will see that if you apply the same thing and you multiply the K by this signal and you get this, okay? If you try to use the same integrator, let's see. First we go to minus 2 and then we go 0. But then we go plus 2, right? This, right? We go plus 2. If we go plus 2, then we go back to 0, right? And then we go plus 2 again, which means that we go positive. And then we remain the same. And then we go positive. So, as you can see, you are not always in the same. Yes. So you go down and then you go up again. Okay, that's because you are using a key that's shifted. So this shows you that even if you use the same key that's shifted a little bit, you misynchronize. Missynchronization Cdma is very critical. Then this data will be misinterpreted as, remember, it's positive. For using the integrator output, the integrator output is positive, then this means that the original data was 0, right? Because positive means 0. Then we will interpret this as wrongly 0. Remember, neither AD nor BD starts with 0 أصلاً يعني. Okay, so this will allow you to, and this one is, interestingly enough, you stay at 0, which means that you don't even know whether it's positive or negative, just by shifting the key a little bit. So synchronization is very important in that case. So the receiver has to be completely in sync.
So why do we need an integrator here?
The integrator is basically the summation. The integrator corresponds to the fact that you sum the values of all the bits.
So before the digital signal is also a composite signal. It's in a digital format. Like the AS plus BS into K, that is also a composite signal expressed in digital format.
Yes, exactly.
So from that, why can't we recover the original signal with the...
How? Using the integrator. This is the only thing. Because remember, these 6 bits, this 6-bit duration corresponds to only 1 bit of data. So how do you extract the original bit of data? They usually use the integrator. The integrator is just tries to sum all the values of all these 6 bits. Yeah. So if the answer is positive, this means 0. If the answer is negative, it means 1. Okay. Type. That's so I think I don't know. Do we have time to go for this? I don't know. I think it's enough for now. We have 2 slides and then we'll go to the next chapter. But this I think it's enough for today. I was hoping to finish these 2 slides, but